So I'll display the question for a minute and then you guys can work out the answers. Once you get the answer, you can tell it loud. And once when majority of you get the answer, we can proceed with the solution and I'll explain the solution. So let's begin with the first question. Determine the Nyquist rate for the signal x of t is equal to 1 plus cos of 100 pi t plus sine of 200 pi t in samples per second. So first think about what is Nyquist rate. I'll give you a few seconds to understand the question. Then I'll tell you the answer. If anybody has found the answer, you could tell it loud. We could discuss. I'm expecting an interactive session, guys. Only then you could. Yeah, right. So only if you guys come, speak out, tell the answers, ask your doubts. Only then this 1 hour is going to be useful for you. So I'm here to help you. Yes. So let's go on to the solution. The answer is 200. So let's see how. First, what is Nyquist rate for a signal? Basically, the Nyquist rate should be twice the maximum signal frequency. So, if we see the signal x of t, it is 1 plus cos of 100 pi t plus sine of 200 pi t. So, how does this signal look in the So, how does this signal look in the frequency domain? Okay, 1 second. Yeah. So if we see, we'll have impulses at 0 hertz because there's some issue with my writing, I'm not sure. So that we'll have impulses at 0 hertz, and then because of cos of 100 pi t, I'm going to have some impulse at minus 50 and plus 50 here. So cos of 100 pi t means I'll have half and half here. And then I have sine of 200 pi t. So now I'll be having we'll have another set of impulses, one at minus 100 and the other at plus 100. So this will be 1 by 2j and that will be minus 1 by 2j. So this is the signal representation in the frequency domain. Now what is the maximum frequency of this signal? It is 100 hertz. So the Nyquist rate is twice the maximum frequency. So the answer is 200 samples per second. So when you are asked to find the Nyquist rate, you have to first try to understand the frequencies present in your signal. Then list out all the frequencies. Find which is the maximum frequency. Then your Nyquist rate will be twice the maximum frequency. Are you guys clear? Are you guys able to follow what I'm telling?
Yes, ma'am.
Yeah. Okay. Let's move on to the next question. We have an audio signal with one-sided bandwidth as 12 Hz and it's sampled at Nyquist rate and quantized to 8 bits per sample. So, what is the data rate of the quantized stream? So you have to find the data rate. So try to understand the question. Think about how to find the data rate. If you get, yes.
192 kbps.
Okay, yes. Let us give few more seconds for others to understand the question. Others, think about how to find the data rate. Okay, let's move on to the answer. So the answer is 192 kbps. Yes, he was right. So how do you find the data rate? So you should first know the sampling rate and then into how many bits you have per sample. So how do you find the sampling rate? They've given that it is sampled at Nyquist rate. So we have the bandwidth as 12 kilohertz. So our sampling rate is going to be 2 into 12k samples per second, and they've given that it is quantized to 8 bits per sample. So we have 8 bits per sample into 2 into 12k samples per second. So ultimately 8 into 2 into 12k, we are going to get 192 kilobits per second. Is anybody having any doubt in this question or how to solve it? See, if you get an idea of how to solve these questions, then it is going to be very helpful for you to solve the assignment questions that are to be graded. So this is just what to say, an example kind of a questionnaire to solve that set of questions. Okay, so can we move to the next question? So using a 8 PSK modulator, how many bits is going to become one symbol? Using an 8?
3.
Yeah,
3.
right.
3.
Yeah, so the answer is going to be 3. Basically, when you have a memory PSK, you're going to have m phase shifted versions of the carrier to transmit the data. So basically your m will be 2 power n, and when it is a memory PSK, it means that you can turn 3 bits to one symbol. Right. Now, you have a 16 QAM constellation here. What is the average symbol energy? Can you guys work it out? Basically, the constellation is given here. What is the average symbol energy?
Symbol energy means?
Yeah, symbol energy means, see, you have 16 symbols here, right? So, find the total energy. So, one second. Yeah. So, find the total energy divided by how many symbols we have. Totally, we have 16 symbols in a 16 constellation. So, if you take this symbol, whatever I am showing here, sorry. So, it is 1 plus 1 So, what will be your energy? 2. Same way for this left side symbol, it is minus 1 plus 1 Again, your energy is going to be 2. So, you have 4 symbols that are going to have energy 2. Same way, find the energy for each of these 16 symbols and divide it by 16. So that will give you the average symbol energy. Are you guys able to follow what I'm telling?
So the right side top symbol,
yeah,
energy is, if it is 3 and 1.
3 and 1. Okay, this one. Yeah.
Sorry, y-axis 3 and x-axis 1.
Okay, okay.
So the energy is 4 4, is it?
No. So it is root of 3 square plus 1 square.
Okay.
So I mean the whole square. So the energy is going to be 9 plus 1 10. So the energy of that is going to be 10. Got it?
Yes.
Yeah. So I told you you have 4 symbols of energy 2. Then think about how many symbols like this you have with energy 10. So 1, 2, then
4.
3. No, you will have more. 3, 4. Then you will have another one here 5. Then you have 6. Then again 1 comma 3, 7, and then 8. So you will have 8 symbols of with energy 10.
80.
Yeah.
And energy, this is 18.
Yeah, and then you have to find for these 4 now.
We have 4.
Yeah.
72 plus 80, 152 plus 8.
Ma'am, 10.
Yes.
Answer.
Yeah. Right. So the answer is 10. So this is how you find the average symbol energy given any constellation. Okay, try to find the energy for one symbol and try to sum it up, sum all the symbols energy divided by total number of symbols. Is anybody having any doubt?
In the real world, how this energy will be useful, madam, actually? In the real world, say suppose
Okay.
I take a signal, I mean, if I'm modulating a signal
Okay.
with 16 QAM,
Yeah.
does it, I mean, what exactly it signifies? Actually?
Yeah. So in these kind of energies, like with what I know, have you heard about this PAPR? So there is this term called PAPR, which is the peak to average power ratio. Okay. So when you send a signal, this peak to average power ratio should be minimal. That is the peak power to average power. So if you see for the 16 QAM, now what was the peak power? It was 18, right? And peak energy. So in a sense, so 18 and then the average energy was 10. So if the peak to average power ratio is larger, what happens is the power amplifier at the transmitter end is going to enter non-linearity and it's going to cause so many problems. So that is why the symbol energy is something which is important. So what is the average symbol energy and how much each symbol is above the average symbol energy. So that is important in the power amplifier perspective. Got it?
Yes.
Yeah. Okay. So this is the magnitude response of some signal called x of t.
Madam, can you mute everyone? I mean, there is an echo coming.
Okay, guys, can you mute yourself because I have to go to that screen to mute you guys.
Prasanna, yeah, fine.
Yeah. So the magnitude response of x of t is given here. So the left one is the real part and the right one is the imaginary part. So what is this x of t signal? Is it a baseband signal? Is it a real signal? Is it a passband signal? Real or complex? So what is the signal x of t? So this left A1 is the real part and the right one is the imaginary part.
Don't know, madam. Not sure.
Okay. So I'll guide you guys to the answer. Now, if we see that this spectrum is centered around Fc. What does Fc mean? Fc is the carrier frequency. So this spectrum, the real and imaginary part of the spectrum is centered around the carrier frequency. So this signal is a passband signal. So what do you know the difference between baseband and passband? Passband signal means you have you've modulated the signal over the carrier frequency. So your signal is centered around the carrier frequency, means it's a passband signal. Now, so basically your option gets boiled down to C or D. Now we have to find whether it's a real signal or a complex signal. So how do you find a real signal? So when your x of t, so when your x of t, sorry for my poor writing guys, my pen is having some issue. So if your x of t is equal to x conjugate of minus t, that is if your x of t is conjugate symmetric, then it means it is a real signal. So when your x of t is equal to x conjugate of minus t, then your signal is a real signal. Basically, if it is conjugate symmetric. So if you see the imaginary part B, this imaginary part, so your x of minus t is x conjugate of, your x of minus t is basically x conjugate of t, if you see. So this signal is going to be your real signal. So the answer is it's a real passband signal. So basically it's centered around Fc, so it's a passband signal. Then the magnitude spectrum is conjugate symmetric, that is your x of t is equal to x conjugate of minus t. If you see, you have to look into the imaginary part to understand this. Then your signal is actually a real signal. So the answer is option C. Is this clear, guys?
Yes, yes.
Yeah.
Ma'am, a doubt for baseband signal for FC, is it would be FM? FM?
Yeah, it will be FM, right. Okay. So let us move on to the next question. Pulse shaping in a communication system is used for dash. So what do you understand or what do you know about pulse shaping? What is it used for? Is it used for ISI removal or improving bandwidth efficiency, frequency offset correction, none of the above?
ISI removal.
Yeah, it in turn helps to reduce ISI, but by direct definition, pulse shaping is to improve the bandwidth efficiency. How means, see, why do you do pulse shaping basically? So you restrict the bandwidth of your signal, right? So you restrict the effective bandwidth that is being used for your signal transmission. Hence, what happens is it improves the bandwidth efficiency so that your signal is not leaking to your nearby frequencies. Hence, it improves the bandwidth efficiency. Really, its impact is to reduce ISI definitely, but the direct definition we could say it is to improve the bandwidth efficiency.
Okay, thank you.
Yeah. Can I move on to the next question? Okay. Which of the following comments about statement 1 and 2 hold good? So it's about fading. So statement 1 is fading causes fluctuation in your signal strength. In your signal strength. Statement 2 is rate of this fluctuation depends upon Doppler. So whether both are true or statement 1 is true and 2 is false, which of the following options is correct?
Statement 1 is true.
Okay. Okay. So actually the answer is you can say that both are true. I'll tell you how. So right, fading causes fluctuation in signal strength. Generally, fading, you could say that it is a time variation of the received signal power due to changes in the transmission medium or paths. That is, if it's a fixed scenario, that is, if nothing is moving, then fading could be because of the atmospheric conditions like rainfall and so on. If it's a moving scenario, then the movement or the what do I say, the obstacles in your path is going to cause fading. Now, this fading is of can be divided into two categories. One is called fast fading, the other is called slow fading. It's also called as like the fast fading is also called as large scale fading, and slow fading is also called as small scale fading. So this large scale fading is caused because of the path loss, shadowing effects and so on. This slow fading rate, it is caused because of the multipath delay spread and Doppler spread. So the fluctuation because of fading also depends upon Doppler. So if you see this slow fading, I think I've interchanged it. So fast fading is called as small scale fading. So if you see this fast fading, which is this glitches, it is because of the multipath delay spread and Doppler spread. So the fluctuation because of fading depends upon Doppler also. Did I confuse you guys, or is it clear?
Clear.
Okay. So I'll move on to the next question. Now you have a base station. It is transmitting a signal with power of 40 watts. How do you express this power level in dB watts and in dBm? These things are like very important when you have to solve the link budget analysis and so on. So you should be very careful with the units.
So 10 log 40.
Yeah, so 10 log 40 will be what? dB watt? Will it give dB watts or dBm?
dBm.
10 log 40, 10 log 40 dB watt.
Yeah, it's actually dB watt. So that's the minute difference. So if you want to tell it in dB watts, it is 10 log of 40 watts. Okay, that is power in watts. If it is dBm, then it is 10 log of power in milliwatts. So you should write 10 log of 40 into 10 power 3. So if it is 40 watts, in dB watts, if you have to write, it will be 16 watts. Okay, 16 dB watt. I'm sorry, there's a typo. So it will be 16 dB watt. Then if it is in dBm, it is 10 log of 40 into 10 power 3. So it will be 46 dBm. You have to remember with this m. If it is dBm, it is power in milliwatts. 10 log of power in milliwatts. Is it okay, guys?
Clear, ma'am.
Yeah. Okay. Now you have a 4G cell phone with front end receiver bandwidth as 20 megahertz. So your bandwidth is 20 megahertz and it's operating at 27 degrees Celsius. The cell phone has a noise figure of 3 dB. And the receiver sensitivity of the phone is given as minus 125 dB watt. What is the minimum required SNR to detect the signal? So try to think about the formula for SNR and try to see how you will use these values. So you have bandwidth, temperature, operating temperature, noise figure, receiver sensitivity. Okay, so I'll tell you how to solve it. So basically, the formula for minimum required SNR is receiver sensitivity minus receiver noise floor. So, why do you want to find the minimum required SNR? So, when you transmit a signal, the signal is going to get received by the receiver, and there will be a path loss involved in your signal. Then there is going to be some noise at the receiver. Ultimately, to deduct your signal, there is a particular amount of SNR which you definitely need. So, what does this SNR depend upon? It depends upon your receiver sensitivity and your receiver noise floor. So, the receiver sensitivity has been directly given as minus 125 dB watt. Now, receiver noise floor you have to find. So, the receiver noise floor is basically your noise figure plus thermal noise floor. Generally, they will say this as KTBF noise. So, what is KTBF means is K is the Boltzmann constant, which is 1.38 into 10 power minus 23. Sorry, it's a typo. So, it's 1.38 into 10 power minus 23 joules per Kelvin. And your T is operating temperature in Kelvin, and your B is the bandwidth in Hertz, and your F is basically the noise figure. So, how we've split here is the receiver noise floor is the sum of thermal noise floor plus noise figure. So, how do you find the thermal noise floor? 10 log 10 of KTB. So, you know K, you know T. They've given in Celsius, it's 27 Celsius. So, to convert it to Kelvin, you know that you have to 27 plus 273. Then you know the bandwidth is 20 megahertz. Here you have to put it in terms of hertz. Then you directly find the thermal noise floor. After finding the thermal noise floor, you sum it up with the noise figure. So the noise figure has been given as 3 dB. So you directly sum it up with 3 dB, and so the minimum required SNR will be receiver sensitivity minus 125 minus sum of thermal noise floor plus noise figure. So the answer is 2.82 dB. So only if we are able to transmit a signal with some power such that your SNR is 2.82 dB, your receiver will be able to deduct your signal. Okay, let us move on to the next question. What is known as multipath delay spread in a communication system? How do you calculate the multipath delay spread? Whether it is a difference between the time of signal transmission and time of signal reception, or the difference between the time of arrival of the first and the last copy of the transmitted signal at the receiver, or whether it's the shortest distance between two multipath components, or the largest difference between the time of arrival of the two multipath components.
D, madam,
D.
large difference between time arrival of two multipath components.
Okay, is it just the difference between two multipath components?
Okay, multiple copies of data we can get
Yeah,
during multipath.
yeah.
And delay multipath, so delay across all the signals.
First
Right.
and last copy.
Yeah, basically it's P, you're right. So, if you see what causes multipath to us, if this is the transmitter and this car is the receiver, you have multiple obstacles in between. So, you're going to receive multiple copies of the same transmitted signal. So, multipath delay spread will be the time difference between the first and the last copy of the transmitted signal. So, that will be the multipath delay spread. So, the next question is here. We have a 64 QAM modulation and the transmitted data rate is 6 megabits per second. And Nyquist pulse shaping is used. What is the duration of each QAM symbol? How do you find the duration of each QAM symbol?
So bit rate will be 48 Mbps
Okay.
and uh, uh, QAM symbols per second 64 QAM.
So first what you have to find is the frequency. Then you could do 1 divided by frequency of symbols. So how do you find the frequency? It's basically the data rate in bits per second divided by how many bits you have per symbol. So what is our data rate? 6 megabits per second, right? Then how many bits we have per symbol? It's a 64 QAM. So we're going to have 6 bits per symbol. So bits per second divided by bits per symbol, what we're going to get is 1 mega symbols per second, right? So how can you find the time duration of each symbol? 1 divided by this. So you're going to get 1 microsecond per symbol. So to find the duration of each QAM symbol, we are first finding the frequency of the symbols. So it's data rate in bits per second divided by number of bits per symbol. So we have 6 megabits per second divided by 6 bits per symbol. So which is going to become 1 mega symbols per second. And we are doing 1 divided by that to get the time duration of each symbol.
Basically, it is 1 divided by baud rate.
Yeah. Is it okay, guys?
Yeah, okay.
Okay. So the lectures discuss about GSM. We have the question is like this: a user gets assigned 1 time slot per frame, and the gross data rate is 22.8 kilobits per second. What would be the obtained gross rate if if 6 tail bits are converted to data bits in addition to the existing 114 data bits? Generally we have 114 data bits. Now what we are telling is we have some 6 tail bits which are being converted to data bits. So we are going to have 120 data bits. So now how is our gross data rate going to change?
Would remain same.
No. Now we have 6 more bits that have become data, no? So definitely the gross data rate is going to change.
We're talking about gross data rate, right?
Yes.
So the padding bit has been converted into the data now. But still the data rate would be still the same. Maybe effective data rate would vary, like net data rate. But gross
will
data
increase.
No, gross is going to increase, right? Okay, let's do something like a direct variation. So you had 114
5%.
data bits. Now so the gross data rate was 22.8, sorry, 22.8 kbps. Now I'm going to have 120 data bits. So you could even directly look into some kind of a direct variation like this.
It's roughly 5% increase.
Yeah.
So
So it's actually
22.8.
120 into 22.8 divided by 114. But if you want like proper explanation, see how did you get this 20? Generally, you have 114 data bits in GSM, and the gross data rate is 22.8 kbps. So how do you get this 22.8 kilobits per second? First of all, so generally in GSM we're going to have 8 time slots per frame, and there we know that the time duration of one time slot is for approximately 577 milliseconds. No, 0.577 milliseconds. So it's 576.92 microseconds. Now here we'll have 114. So it will be 114 bits divided by 576.92 microseconds. And there is this concept called multiframe. So out of the 26 multiframes, only 24 multiframes will be used. So it is 114 divided by 576 microseconds into 24 by 26. Like that, you have actually 8 time slots. So it's 1 divided by 8. So if you do this calculation, we'll be getting 22.8 kilobits per second. Now instead of 114, we have 120 here. So the calculation. So if we repeat the calculation, we're going to get 24 kilobits per second. So I guess approximately 156 bits will be sending, amongst which 114 is data. Now we have 120 bits to be data. Is it clear? Are you guys getting an idea?
Yes.
Yeah. Okay. Okay. So the next question. We have a cell phone. It has 2000 milliamp mAh battery, and the cell phone draws 500 milliamps of current in the ideal mode and 200 milliamps of current during a call. And the user makes 4 minutes call every hour. So how long is your battery going to last? Okay, so I'll get to the answer directly. Basically, what we are going to find, time for which the battery is going to last, and how much charge is available to 2000 mAh. We know that he's going to make a 4-minute call every hour. So 4-minute call means for 4 minutes he's going to use 200 milliamps, and for the rest of your 56 minutes he's going to use 50 milliamps. So if you find how much current he's going to use up in 1 hour, it is 60 milliamps. So the total charge available is 2000 milliamp mAh. So if you divide both, you're going to get 34 hours. So his battery can last for 34 hours. Straightforward. Is it okay?
Yes.
Yeah. Okay. So a communication receiver performs the following tasks in what order? So generally at the receiver, what all will we do? So you have to do synchronization, offset correction, channel decoding, channel estimation, equalization. So what is the order of the tasks?
C.
Synchronization and offset, channel estimation, channel decoding, equalization.
No, it's C, equalization, and then only we'll do decoding, right? Basically, we'll have to estimate, equalize for the channel effects,
ISD.
and then we'll decode. Yeah. Okay, the major application areas of 5G are,
all of the above.
yeah. So this is just for a thing. So generally, the application of 5G are like in many areas. So some of the areas: enhanced mobile broadband, ultra reliable low latency communication, massive machine type communication. Okay. In a massive MIMO system, beamforming is a concept of dash. Is it a concept of channel estimation? Is it a concept of error control coding, directional transmission and reception, channel equalization? So why do we use beamforming in a,
Directional transmission.
Directional transmission.
yeah? So we use beamforming for directional transmission and reception.